Good morning. Good morning to all of you. Today in this session, we'll be discussing heat engine, Carnot's theorem, and entropy. So, in this one lecture, we'll be covering a lot of things, and these particular topics are very important for the examination. Before I start, let me know if everything is all right. Then we will start the session. Can you hear me properly? We'll start with heat engine. Hear me properly? Start with just a moment. I think a little bit of background noise is coming when I'm talking. We can start today's session. Is everything all right? Let me know. Okay, so let's start with heat engine, Carnot's theorem, and entropy. Or is there any issue? Tell me quickly. So if you start with heat engine, what is a heat engine? A machine that basically converts heat into work. Heat to work. In the first law of thermodynamics, we have seen that. Here is everything all right? Especially the issue, audio issue. Is there no audio issue? Then we can move forward. In the first law of thermodynamics, we have seen that heat, if you apply some heat to a system, that heat is utilized in two ways. One part of the heat is utilized in doing work. Another part is used to increase the internal energy of the system. So, to convert heat into work, we use a machine that is called heat engine. It is a system that performs the conservation of, it is conversion. Perform the conversion of heat, conversion of heat or thermal energy to mechanical work. So, in this example, a standard heat engine has been shown to you. Heat is going, we have a boiler, then with the help of turbine, get the work output. Okay. So, in a standard heat engine, we see few various components, like we have hot reservoir, then cold reservoir, and some working agent in between. The basic structure of a heat engine. We have this hot reservoir, which is maintained at some temperature T1, and we have a cold reservoir, which is maintained at some temperature, let's say T2. So, hot reservoir and cold reservoir, so obviously this T1 must be greater than T2. This thing you need to keep in mind, and this is the working agent, maybe steam. Here you can say it is taken to be steam. So, the working substance, you can. So, heat will be taken from the hot reservoir and it will be given off to the cold reservoir. Let's say if heat is taken from the hot reservoir is Q1 and heat given to the cold reservoir is Q2, obviously Q1 and Q2 are not same. In between, it is also performing some work. So, from the equivalence, you can say Q1 plus Q2. Q1, it is utilized in two ways. Q2 plus W. From here you can see, and hence we get the effective work done to be equals to Q1 minus Q2. So, you can imagine it, this work done is the effective work done we get in this, let us say, heat engine. This Q2 is the heat given to the surrounding. So, sometimes this hot reservoir is termed as source and this cold reservoir is termed as sink. Sink may be, it may be surrounding or anything else, and this is the effective work done we get. So, Q1 is equals to Q2 plus W, that is W is equals to Q1 minus. Good morning, Ajay. Now, this is the basic structure of a heat engine. We have to define the heat efficiency, the efficiency of this heat engine. How will you define efficiency? Let us define efficiency of this heat engine. Efficiency is denoted by eta. Efficiency, which is denoted by eta, of a heat engine is defined as the ratio of the work done by the engine during one cycle to the heat taken in from the source in a cycle. So, you can imagine efficiency, it is like the ratio of the output and the input. You need to understand very clearly what is the effective output, what do you want, that is the output, and what we give, that is the input. So, in a heat engine, our main purpose is to get some work done. So, this is the output, and what we are giving as input, we are giving this heat from the hot reservoir, it may be some kind of boiler. So, we are taking in heat. So, this is the input and this is the output. Now, this amount of heat Q2 which is given to the sink or cold reservoir, that is surrounding, actually this is a loss. So, how effectively it is able to convert the heat into work, and that is actually giving you the quantitative measure of the efficiency eta of the heat engine. Yeah. So, mathematically if we define this eta, so eta is the ratio of the work done W divided by the heat taken in, so that is Q1, and W we have already seen, it is equals to Q1 minus Q2 divided by Q1. So, this is 1 minus Q2 upon Q1, and obviously this Q1 is the total heat. Q2 will always be less than Q1. Okay. Q2 is always less than Q1. So, this eta factor will always be less than 1. 1 minus some finite value. So, eta will be always less than 1. Since Q2 is less than Q1, eta is less than 1. So, when you get the maximum efficiency you achieved when Q2 is 0. Q2 is 0 means no heat is given to the surrounding. It's like you are burning coal and you are doing some work. Okay, say you are heating some water and you expect no heat goes to the surrounding. That doesn't happen, right? So efficiency equal to 1 is impossible. If Q2 is equals to 0, then eta is equals to 1, which is not possible in practice. Some heat will always go to the surrounding. And this means the heat engine cannot convert all the heat taken in from the source into work. Clear? Later on we will see that this Q1 and Q2 ratio, Q1 by Q2 is equals to T1 by T2. So Q and T are equivalent, we will see later on. Then we will see that eta is equals to 1 minus T2 by, where T2 is less than just a moment, guys. Murli, is it Clausius statement? Yes, in one way you can say it is given in the Clausius statement. It is impossible to convert all the heat into work. Yes, all right. Heat engine is a, you can say, direct representation of the second law of thermodynamics, direct consequence of the second law of thermodynamics, or you can also say that the second law of thermodynamics is a direct consequence from the result obtained from heat engine. Okay, now we have talked about this heat reservoir. Let's talk about it a little bit more. I think you know what is heat reservoir. Do you know anything about heat reservoir? What do you understand? Can you tell me, guys? Murli, Ajay, Hari, and everyone, what is heat reservoir? What do you understand by that? Heat reservoir is you can say infinite pool of thermal energy. If you take some heat from that, or if you give some heat to that, it will not, there will be no change in temperature. It is like a sea. Okay, na? If you put one bucket of water into the sea, or if you take one bucket of water from the sea, the water level does not change. Okay, it is very negligible. It is like that. In a heat reservoir, it is effectively an infinite pool of thermal energy at a constant temperature. Heat reservoir will maintain some constant temperature. its heat capacity is so large that when it is in thermal contact with another system, its temperature remains constant. All heat engines have three essential components, as you can see: a watt reservoir or source, working agent, and sink. A source, this is a hot region that is a part of the surroundings from which energy flows by heat transfer. It is popularly known as hot reservoir, example in a nuclear reactor or furnace. Working agent, this undergoes changes in state as part of the continuous cycle, example steam water. A sink, this is a relatively cold region, that is part of the surroundings into which heat is rejected through heat transfer. The rejection of heat into sink does not increase the temperature due to its large heat capacity. So, if you are, let us say, boiling some water, the heat from the burner, will it increase the surrounding temperature? No. The surrounding atmosphere, you can say, it can take up infinite amount of heat, it will not increase the temperature. So, effectively an infinite pool of thermal energy. So, I hope you got the concept of heat reservoir. Let us now go to quickly this Carnot's heat engine. We have understood heat engine. Now, Carnot gave an ideal heat engine from where you can get the maximum efficiency. The efficiency cannot be enhanced more than the efficiency of a Carnot's engine, and that is also one way a statement of Carnot's theorem. Carnot's ideal heat engine. It is a theoretical thermodynamic cycle proposed by Nicholas Leonard said Carnot. One person, Nicholas Leonard said Carnot. It can be shown that it is the most efficient cycle, means efficiency is maximum for converting a given amount of thermal energy into work. A system undergoing a Carnot cycle is known as Carnot heat engine. Stages of the Carnot cycle. So, for the time being, you see here we have represent pressure, then volume V. So, it consists of 4 stages. From A to B, you can see it is carried out by isothermal expansion. So, you are expanding the gas, let us say, in an isothermal process. From B to C, adiabatic expansion. From C to D, isothermal compression. So, in this direction, if you are going, if it is expanding, in the opposite direction, it will compress. And B to C, you can see it is adiabatic expansion. And you can get it from this direction. If you are going along this direction, volume is increasing. Volume is increasing means expanding. Volume is decreasing means compressing. So, D to A, you are going, you can say in one way it is volume is here, here the volume is here. So, you can see the volume is decreasing. So, it is adiabatic compression. So, it is composed of these 4 stages. Let us just draw this with some more detail on this slide. So, this cycle is known as Carnot cycle. So, we are taking help of the PV diagram. So, let us say we have a system or gas which is initially at point A, and it has, let us say, it will have its PV values. So, let us say that is P1, V1. Now, from A to B, it is going, let us say, is going to B, and here P2, V2, and during this process you can see it is said that it is an isothermal expansion. So, let us consider that it is maintaining a constant temperature T1, isothermal. Then from B to C, it is going via adiabatic expansion. So, here let us say the pressure volume values are P3, V3. So, let us say now from C to D, it will go via isothermal compression. maintaining a constant temperature. So, that is why we are giving it a constant temperature of T2, and from D to A, it is going via adiabatic compression. So, the first process is isothermal expansion. Isothermal expansion. So, if you have expansion in a gas, what you have to do? You have to give in some heat, right? So, here in this process, let us say Q1 amount of heat is given to the system. So, this is we are talking about Carnot's ideal heat engine. So, we are giving it a mathematical treatment. It consists of 4 processes. The first process is isothermal expansion. The first process, process 1, is isothermal expansion. So, this process are being carried out to the working agent. It may be some gas or steam, anything. So, let us consider gas. So, it will be clearer or easier to imagine. So, isothermal expansion is represented in this AB. Let us also write the part AB. The isothermal expansion AB of the working substance and the isothermal heat transfer from Q1 will be given to what? From what reservoir to the working agent? From the hot reservoir to the working agent. One thing I missed to mention here, you can see the efficiency is given by 1 minus Q2 by Q1 or 1 minus T2 by T1, we will see later on. So, it does not depend on the working agent. Okay, so, we can also write note, let us say this is 1 and this is 2, the efficiency of a heat engine is independent of the working agent or working substance. Okay. So, you can use some gas or steam, the efficiency will not change. It will only depend on the temperature of the hot reservoir and the cold reservoir. Okay. So, look at this process. Process 1 is the isothermal expansion AB of the working substance and the isothermal heat transfer from the hot reservoir to the working substance or agent. Where you write? You have written already agent, you can write. You have not written, you can write substance. So in this process, you are giving some heat to the system, so there will be change in entropy, and you know entropy always increases. So the gain in entropy in this process is, can you tell me, delta S will be integration from A to B dq by T. Let's consider that it is taken by a reversible process. You know, we have used the mathematical form of second law of thermodynamics. So what is the change heat transfer? It is Q1, and what temperature it has been carried out? It is T1, so it is Q1 by P1. This is the gain in entropy. And since it is maintained at a constant temperature, since it is an isothermal process, change in internal energy will be 0. So therefore, and work done will be, work done, let's say it is W1 for process 1, work done is W1. We have already evaluated this. Sorry. nRT ln V2 by V1. This is the formula. Here T is equals to T1, so nR T1 ln V2 by V1. Can you write it? So from here we can get the value of Q1. What is Q1 then? Change in internal energy plus the work done. So that is nR T1 ln V2 by. So let's save this. This will be used later on. Let's go to the second process, process 2. Process 2 is what? Adiabatic expansion. Adiabatic expansion. As the name suggests, adiabatic means there will be no heat transfer. This is adiabatic expansion. So what is happening in adiabatic expansion? This is a reversible. So this is a reversible engine, okay? Carnot's ideal heat engine, we can say that it is a reversible engine. Reversible heat engine means these processes are being carried out in a very slow manner. So process 2 is reversible adiabatic expansion. Of the working substance here delta Q no equals to 0, no heat exchange. So, we can say Q2 is equals to 0. Okay, delta Q is equals to 0, that. So, if delta Q is equals to 0, from the second law of thermodynamics, we can say delta S is equals to delta Q by T. So, if delta Q is equals to 0, so there will be no change in entropy. So, the entropy remains constant in this process of reversible adiabatic expansion. Delta S is equals to 0. What does it mean? This is called isentropic process. Isentropic process, where entropy remains constant. And this is a reversible process. Okay. Now, here heat exchange is 0. What about the work done? Work done is, let us say we are denoting it by W2. So, we will have to use the formula of adiabatic work done, that is 1 by 1 minus gamma into NR T2 minus T1. You can see final temperature is T2, initial temperature is T1. So, this is the work done. Okay. So, to find out the efficiency of the heat engine, we require work done. So, let us highlight this work done in each step. So, this is process 2. Process 2 is done. Let us go for the process 3. Process 3, what is happening? It is again isothermal compression. Okay. This is about isothermal compression. So, here it is like the sink. Let us say the heat transfer is Q2. Third process, process 3. Isothermal compression, and this is between A, B, C, C, D. What is happening in isothermal compression? This is your reversible isothermal compression. So, delta U will be 0 here. And what about delta S? E to D dq upon T reversible. Here the heat transfer is Q2. Look, now here should I use plus Q2 or minus Q2? Try to understand it very carefully. What is happening? Hot reservoir, it is giving off the heat, right? Q1 is given off by hot reservoir. For cold reservoir, Q2 is accepting the heat. So, we have already told you the sign convention of heat transfer. If heat is given off, Q is positive. If heat is accepted, Q is negative. So, we are going to use that sign convention here. So, it is temperature is T2. You can see for CD, what is the temperature? T2. So, we have put T2, then integration T to D, what amount of heat is transferred, that is you can say minus Q2 by T2, because heat is absorbed here. Is this clear? So, yet what will be the work done? Let us say W3 third process, it is an isothermal process. So, nRT ln V2 by V1, nRT is T2 here, ln V2 by V1, V2 is the final temperature, V1 is the initial temperature. As you can see here, we have taken P1, V1, P2, V2, P3, V3. So, let us call this D, it has this P4, V4. Okay. So, V4 is the final volume, V3 is the initial volume for this process of isothermal compression. So, what you will write here? ln V4 by V3. So, the heat transfer here Q2 is equals to change in internal energy plus W3, that is nRT2 ln V4 by V3. We require this W3. Q is also required to evaluate the formula. Okay. Let us go for the fourth process. You can name it process 4, that is adiabatic compression. This is happening between D to A. For adiabatic compression, what is happening? This is सारे कलर्स खत्म हो गए दोस्तों, ब्लू ही बाकी है, ब्लू को ही. Here we have the reversible adiabatic compression of the working substance. So, therefore, we can say there is no heat transfer, delta Q is equals to 0. So, delta S is also 0. What will be the work done here? We will denote it by W4. So, this is a reversible adiabatic work done. The formula is nR T2 minus T1. Here, what is T2? T2 is the final temperature here. So, for this process, you are going from D to A. The initial temperature you can see T2. What is the final temperature? It is T1. So, you have to write T1 minus T2. Is it clear till now? Tell me, guys. What we have to calculate? We have to calculate efficiency of the Carnot engine. Therefore, the efficiency of the Carnot engine is given by eta is equals to W by Q1. This is the formula, right? What is W here? W is the work done during the cycle. That is, W is equals to the sum of W1, W2, W3 and W4, and Q1 is the heat given to the system. So we have individually calculated W1, W2, W3 and W4. Let's just add them up. As you can see, W2 and W4, they are equal and opposite. W2 and W4, here we did not write it, right? Adiabatic, so thermal expansion, adiabatic expansion, and here we have adiabatic compression. So let's add all of this work done, then what you will get? W is equals to, what was W1? W1 was nR T1 ln V2 by V1. W2 is 1 by gamma minus, 1 by 1 minus gamma nR T2 minus T1. Okay, what about W3? W3 is nR T2 ln V4 by V3 plus, this is 1 by 1 minus gamma nR T1 minus T2. So we can see that this term and this term is cancelling. We are left with this 2. nR T1 ln V2 by V1 plus nR T2 ln V4 by V3. Q4 is not mentioned in the process. This is not Q4, delta Q is equals to 0. Actually, our main interest is Q1 and Q2. The other two processes are adiabatic process, so there will be no heat exchange. Q1 is equals to, what is the value of Q1 we have got in the first process? nR T1 ln V2 by V1. nR T1 ln V2 by. So from this we can calculate the efficiency eta. Eta is equals to W upon Q1. So W upon Q1 is equals to this. You can see this nR T1 ln V2 by V1 is this. We can write 1 plus nR getting cancelled, T2 by Q1 into ln V4 by V3 divided by ln V2 by . Now you can see, if you talk about this B to C, what is the process? It is adiabatic expansion. For adiabatic expansion, you know, PV to the power gamma is equals to constant. So that directly means TV to the power gamma minus 1 is equals to constant, right? Now we have to remove this V4 by V3 divided by ln V2 by V1. So to do that, we know that for an adiabatic process, PB to the power gamma is equals to constant. So if you put PV is equals to RT by P is equals to RT by V, so you get T V to the power gamma minus 1 is equals to constant, right? So we are applying it from for the path of BC. So if I apply for BC portion of the curve, as you can see, we can say that initially the temperature was T1. What was the volume? V2 to the power gamma minus 1. Look at the point B and C here. B, here the pressure is P2, volume is V2, temperature is T1. So if T V to the power gamma minus 1, so T1 V2 to the power gamma minus 1, and here T2 V3 to the power gamma minus 1. Okay. And if you consider the other process for A, B, C, D, DA. DA is another adiabatic process. So where the temperature is T2. So T2, what is the volume at D point? It is V4 gamma minus 1. A, here the temperature is T1, volume is V1 to the power gamma minus 1. I hope this is understood by everyone. If I call it, let's say, equation number 1, if I call it equation number 2, so if you take the ratio, if you do 1 by 2, what you get? T1 by T2 is equals to T2 by T1. Acha, we can write it on the other way, or on the other way around. To cancel the temperature dependency, T1 V1 to the power gamma minus 1, let's write the right hand side to the left and left hand side to the right. Now we take a ratio of 1 and 3. So if you divide 1 and 3, what do you get? V2 upon V1 to the power gamma minus 1 is equals to V3 upon V4 for gamma minus 1. That directly means V4 by V3 is equals to V1 by V2. And here you can see ln, therefore we can say eta is equals to 1 plus T2 by T1 ln V4 by V3, and here you can see it is ln V2 by V1, but V4 by V3 is equals to V1 by V2. So let's write it as minus of ln V1 by V2, and write it in the denominator. If you introduce a minus sign, we can write, instead of V2 by V1, we can write V1 by V2. Now ln V4 by V3 is same as V1 by V2, so this we can cancel. So we can write 1 minus 2 on T1. So we can combine this result as eta is equals to 1 minus Q2 upon Q1 is equals to 1 minus T2 upon Q1, and hence we can conclude that therefore for a Carnot cycle, Q2 by Q1 is equals to T2 by T1. Or you can write the other way around, Q1 by Q2 is equals to T1 by the efficiency of the Carnot's engine does not depend on the working substance. It only depends on the absolute temperature, not the normal temperature. You have to write the temperature in Kelvin. It only depends on the absolute temperatures of the source and sink. So based on this observation, a theorem is given which is known as Carnot's theorem. So let's talk about that. You must have understood what is there in the Carnot's theorem. This is the most efficient cycle, remember, because this is a reversible cycle. So this will produce the maximum efficiency. You cannot obtain more efficiency than that of the efficiency of the Carnot's cycle. So you can write this Carnot's theorem. It is given by no engine working between two given temperatures can be more efficient than a reversible engine working between the same two temperatures. And that all reversible engine working between the same two temperatures have the same efficiency. Whatever be the working substance. Whatever be the irrespective of the working substance. Let me know when it is done. Achha, this language, whatever be the working substance, you can just change it. I think if you write regardless of the working substance, then it will be more clearer. It will be clearer in meaning. Regardless of the working. The next thing is Carnot's ideal refrigerator heat pump. Heat pump is just the opposite of the heat engine. Carnot's ideal refrigerator. Fridge is called heat pump. If I just show you the picture, then it will be more clear to you. So as usual, there will be some hot body, there will be cold body, and the working substance in between. But here the thing is, you see hot body which is maintained at temperature T1, cold body which is maintained at temperature T2. So here the reverse thing happens. Heat taken in from the cold body given to the hot body. So this is not natural. We have seen in the limitation of the first law. It is not natural. Cannot transfer cold heat from cold body to hot body without the expenditure of the work. So we have to use some work. You are, let's say, you want to extract Q amount of heat and produce Q1 amount of heat. And remember, hot body is always temperature greater than the cold body temperature. So what is happening in this ideal heat refrigerator? In refrigerator, a working substance takes in heat from a body at a lower temperature as a net amount of work done on it by an external agent with the help of electricity and gives out a larger amount of heat. Heat and energy are interconvertible, gives out a larger amount of heat to a hot body. And here the working substance is called refrigerant. So from the figure, you can easily say that Q2 plus W is producing Q1. So W is equals to Q1 minus Q2. So here if you take Q2 common, you can write Q1 by Q2 minus. So if you talk about the performance, how will you decide the performance? Performance is decided from the desired output and the input you are giving. Okay, if the more desired output you are getting, means the performance is good. If the desired output is not so much good, the performance is not so good. Okay, so here what is the input and what is the output? Can you tell me? Here as an input you are giving the external energy. It is the input, na? You are giving external energy. What is the output? What is your ultimate goal? To cool the food items, right? Or to make ice cream. So to extract heat from water to make it ice cream, to keep your food items at very low temperature so it doesn't get spoiled. So our ultimate goal here, the output is to extract this Q2. So this is the output and this is like the input. Understand? In this way if you think, then you will not forget. For heat engine, what was our ultimate goal? To get as much work as possible. For refrigerator, what is our goal? Our goal is to cool the food items with less amount of electricity. This is our goal, right? So here in refrigerator, instead of efficiency, we define it called coefficient of performance. So here also if you let's say use an ideal gas as a working substance, for that case you can write Q1 by Q2 is equals to T1 by T2. So W we can write as Q2. Q1 by Q2 is equals to, you cannot put Q2 is equals to T2, okay? You can only put the ratio. Q1 by Q2 is equals to T1 by T2. Understand? We have not replaced Q2, we have kept it as it is. We have just replaced the ratio. So here our ultimate output is Q2. Input is work done, Q2 by W. So this is equals to, you can see, is T2 by T1 minus T2. This is called the coefficient of performance. You see, the purpose of the refrigerator is to remove as much heat Q2 as possible from the cold body with the expenditure of a little amount of work with the expenditure of as little amount of work as possible. Okay, so this thing is represented by the coefficient of performance. Now we can find out the ratio of this coefficient of performance and the efficiency. So we can say, if we want to define what is coefficient of performance, that is, we can say it is the ratio of the heat taken from the cold body to the work required to run the refrigerator. Now let us try to find out a relation between eta and k. So first of all, eta we had 1 minus T2 by T1, and k we have just got T2 by T1 minus T2. So if you just divide both numerator and denominator by T2 by T1, if you divide both numerator and denominator by T1, what you get? This is T1 by T1 is 1, T2 by T1. So you can see k is equals to T2 by T1. From here, T2 by T1 is equals to 1 minus eta, right? So k is equals to T2 by T1 means 1 minus eta divided by, this is eta. Or you can say eta k is equals to 1 minus eta, and we can say that eta times 1 plus k is equal to 1, and eta is equals to 1 upon 1 plus k. So which one is greater, eta or k? So we cannot do that comparison, but here one thing is clear. If you forget which relation you need to know, k is equals to 1 minus eta by eta, and eta is equals to 1 by 1 plus k. You see, eta is equals to 1 by 1 plus something. So it will obviously less than 1. Eta is always less than 1. So in that way you can remember. If it becomes 1 minus k, then eta would have been greater than 1. So this is, in this way you can remember this formula. Eta is equals to 1 by 1 plus k. Make sure that eta is less than 1. Then you will not forget the formula. Okay. Is there any question till now? Tell me, guys. If not, then we can go for problem. Theory part is almost over. The main theory part we have already done. Is the time for some problem. Sink and cold reservoir are same basically. Hot reservoir is like source and cold reservoir is like sink. Sinks means it will give off heat. Sink means it accepts heat or takes in heat. Just remember this one. Any more question, guys? Quickly tell me. Look, one thing I would like to tell you here. Whatever portion you study, let's say gas or anything else, that is called a system. And whatever we have in the universe other than the system, that is called a surrounding, right? And system and surrounding makes the universe. So total entropy change is equals to the entropy change of the system and the surroundings. Remember this one. Let's solve a problem. The mass m of a liquid at temperature T1 is mixed with an equal mass of same liquid at temperature T2, which is less than T1. The system is thermally insulated. What will be the change in entropy of the universe? Look, as this process is being carried out in a thermally insulated container, so the entropy change of the surrounding is 0. We can say, can you say that? Because it is thermally insulated, it is not affecting the surrounding. So change in entropy of the universe is change in entropy of the system only. So let's say initially we have some mass of m of liquid at temperature T1 and another mass m of liquid with temperature T2, and they are allowed to mix. So it's just like you are removing the partition. Okay. So T2 is less than T1. What does it mean? It means this is a hot liquid. This is hot liquid and this is cold liquid. So hot liquid will lose heat and cold liquid will heat up. So after some time they will maintain a constant temperature, isn't it? If you mixed two liquids of different temperature, what will happen to them? after a certain time they will mix and they will maintain a constant temperature, let us say T. So, let T be the equilibrium temperature. So, it is like this T1 and this is T2 on a scale. So, T1 and T2 they are maintaining an equilibrium temperature. So, the temperature of T1 will fall to T and temperature of T2 will rise to T. Okay. So, if they are equal mass, same liquid means their specific heat capacity is also same. So, heat rejected by the hot liquid is mc T1 minus T. This one we get from the principle of calorimetry. Heat rejected delta Q is equals to ms delta T. So, mc delta T is T1 minus T, and heat takes in by the cold liquid is mc. What is the change in temperature? T2 is more than T. Sorry, T is more than T2. So, this will be T minus T2. Is it clear? So, MC is getting cancelled. T1 plus T2 is equals to 2T. That means T is equals to T1 plus T2 divided by 2. So, what we have to calculate? We have to calculate what is the change in entropy for the process of this hot liquid coming to temperature T. In this process, what is the change in entropy? And in this process from T2 to T, what is the change in entropy? The total change in entropy of the system will be the sum of these two, and as the surrounding entropy change is 0, we can say this is the change in entropy of the universe. So, we are basically trying to find out the change in entropy of the system, delta S of the system. So, delta S of the system, we can say that it is the sum of delta S1 in going from T1 to T, and another part you will have delta S2, that is from going from T2 to T. Okay. This is the total entropy change of the system. So, what is the entropy change in going from T1 to T2? You know the formula. What is the formula? Integration of dq by T. So, dq is mc dt. This is the dq divided by at what temperature? T, plus what will be this formula here? mc integration, it is going from T2 to T. Here also dt by T. MC if you take common, ln T T1 to T plus ln T T2 to T. ln T minus ln T1, ln T minus ln 2 ln T minus ln, you can see T1 plus T2. We can write T1 T2, right? And this 2 we can take it to the power, that means it is mc ln T square by T1 T2. Now, we have already seen T is equals to T1 plus T2 by 2. Okay, let's write it T by square root of T1 T2 whole square. Can you write it? So this is MC ln T is equals to T1 plus T2 by 2, and this root over T1 T2 will remain as it is whole square. No option is matching. Acha, this 2 we can take. And this is equals to 2 times MC T1 T2 2 root over T1 T2. Okay, I think it is matching with option C or B. B. Actually, this one we have calculated S delta S of the system. So actually this is not the answer. Answer will be delta S of the universe. You have been asked. So this is equals to delta S of the system plus delta S of the surroundings. Delta S of the system we have just calculated, twice MC. This is 0. That is why it is twice MC ln T1 T2 by 2 root over T1 T2. That is matching with option B. Okay. Is it all clear, guys? Now, is this thing positive or negative? You know, if you talk about arithmetic mean, is greater than geometric mean. Arithmetic mean is T1 plus T2 by 2. Geometric mean is the square root of T1 by T2. That means delta S of universe is greater than 1, greater than 0 we can say. And that is a fact. Entropy of the universe always increases. आगे बढ़ा जाए दोस्तों. Is everything all right? Can we move forward? This is a little bit lengthy problem, but it is very easy as you can. Give this problem a try. The heat capacity of the interior of a refrigerator is 4.2 kilojoule per Kelvin. The minimum work that must be done to lower the internal temperature from 18 degrees centigrade to 17 degrees centigrade when the outside temperature is 27 degrees centigrade will be. In case of refrigerator, what will be the source? Source is like the outside temperature. What is sink? Sink is like the food items, temperature of the food items. You can see that is the sink temperature, T1, T2. Can you do this? Ajay, Murli, Hari? Do it quickly. What you are given? You are given the heat capacity. is mc, 4.2 kilojoule per Kelvin. So what is our target? Our target is to reduce the temperature from 18 degrees centigrade to 17 degrees centigrade. So what amount of heat you need to extract in doing so? That will be Q2. The heat removed from the refrigerator in lowering the temperature from 18 degrees C, 17 degrees C is how much? What is the formula? You first need to convert it the low temperature TC, actually T2, 18 degrees centigrade, 18 plus 273 Kelvin. So you are getting it at 291 Kelvin. The temperature T1 of the outside is 27 degrees centigrade. So it is in Kelvin, becomes 300 Kelvin. Okay. So what is Q2? Q2 is this amount of heat which is extracted in lowering the temperature from 18 degrees centigrade to 17 degrees centigrade. So Q2 will be equals to mc into change in temperature. mc is given to you in the question, 4.2 kilojoule per Kelvin. Now T2 minus T1 is 291. Okay. Here you see, when you calculate this mc delta T, here we put the temperature in centigrade, okay, 18 degrees centigrade minus 17 degrees centigrade. So that is why it is 4.2 kilojoule. This is the principle of calorimetry. So here the change in temperature is represented in small t. So you have to keep in mind very small details. And you know, one change of 1 degree centigrade is also the change of 1 Kelvin. So that is also okay. So 4.2. So you have to just convert this 18 degree centigrade, 18 degree centigrade 291 Kelvin. If you write it in this way, then also it is okay. 17 degree centigrade means 290 Kelvin. Okay. So in this way also you are getting the same result. Minimum work. For minimum work, we can use this formula for the minimum work. Q1 by Q2 is equals to T1 by T2. That formula we have already got. So Q2 we have got. Therefore, we can get Q1. Q1 is equals to Q2 times T1 by T2. We know T1 and T2, but we also require the value of Q1. So Q1 is Q2 4.2 kilojoule. T1 by T2. T1 is 300. T2 is 291. So this is approximately 4.33 kilojoule. So Q1, Q2 we have got. Okay, this is Q1 and the heat given off. Sorry, this is Q2. This is Q1 and this is W. So W is equals to how much? Q1 minus Q2. So this is 0.1 kilojoule. That is matching with option D. Is it clear, guys? Tell me. Let's move on to this problem. An air conditioner maintains the room temperature at 27 degrees centigrade while the outside temperature is 47 degrees centigrade. The heat conducted through the walls of the room from outside to inside due to the temperature difference is 7000 watt. The minimum work done by the compression of the air conditioner per unit time is. Are you able to get it or not? These things are very simple. The air conditioner is maintaining the room temperature at 27 degrees centigrade. So, this is the temperature of the sink. 27 plus 273 Kelvin, that is 300 Kelvin, while outside temperature is 47 degrees centigrade. So, here T1 is 47 plus 273, that is 320 Kelvin. The heat conducted through the walls of the room from outside to inside due to temperature difference is 7000 watt. 7000 watt means here heat is coming at the rate of 7000 joule per second. We do not know how much heat is this Q and W. So, we know Q2 plus W is equals to Q1. Coefficient of performance of the refrigerator. We have to find out the minimum work done by the compressor of the air conditioner per unit time in watt. How will you do that? Look, we know the coefficient of performance K, which is equals to Q2 by W, that is T2 by T1 minus T2, and therefore Q2 by W. What is Q2? Q2 is 7000 joule per second. W is W. T2 is 300. T1 320. T2 300. So, work done is 7000 divided by 300 into 20. This 1400 by 3. This will give you around 466.67 joule per second actually. So that is 4.466 watt. So the closest option is 465. We can choose that. Yes, Ajay, option A. Let's do this problem. I hope the last problem is clear. Can you do this problem? A Carnot engine whose lowest temperature reservoir is at 7 degrees centigrade has an efficiency of 50%. It is desired to increase the efficiency to 70%. By how many degrees should the temperature of the high temperature reservoir be increased? We have been given a Carnot engine. Whose low temperature reservoir is at 7 degrees centigrade. So here T2 is the low temperature, 7 degrees centigrade, 7 plus 273 Kelvin. So this is 280 Kelvin. Has an efficiency of 50%. So for this case, eta is 0.50. It is desired to increase the efficiency by 70%. So what should be T1 first that we have to find out. Next, if you want to increase the efficiency, and if you want to make it, let's say eta is equals to 0.70, let's keeping the cold temperature same. Let's say this temperature is T1 prime. So what is the change that you have to find out? T1 prime minus T1. Can you do this? I think it can be solved very easily. Nothing is there in this problem. So for the first case, you can see eta is equals to 1 minus T2 upon T1. So eta is 0.5. T2 is 280 by T1. So 280 by T1 is equals to 1 minus 0.5, that is 0.5, and hence T1 is equals to 280 by 0.5, so 560 Kelvin. So you have got it, 560 Kelvin. If you want to increase this efficiency eta, what you have to do? Obviously, you have to increase T1. If you increase T1, this ratio will decrease, and if this ratio decreases, 1 minus some less number will be more number. Okay. Now for the second case, eta is equals to 0.70. We can say that 0.70 is equals to 1 minus T2 is same, 280 divided by T1. T1, let's say it is T1 prime. So what is T1 prime? T1 prime is equals to, so 280 by T1 prime is equals to 1 minus 0.7, that is 0.3. 0.3, so T1 prime 280 by 0.3. So it's a 3 times of 280. You can see 3 by 10. So this will give you around 933.33 Kelvin. So you know, change in 1 Kelvin is equals to change in 1 degree. So increase in temperature equals to 933.33 Kelvin minus 560 Kelvin. This is 372.33 Kelvin, and this is also equals to the same change in temperature. We are calculating in terms of Kelvin, but the change of the 1 degree Kelvin change and 1 Kelvin change and 1 degree centigrade change is same. So, you can write it as in degree centigrade. 372.33, option A is matching. I am not saying that 50 degree centigrade is equals to 50 Kelvin. It is not like that. The change, if you go from 50 to 51 degree centigrade and if you go from 50 Kelvin to 51 Kelvin, the change in temperature is same. Clear? Let us do this problem. 1 mole of an ideal gas at 300 Kelvin expands reversibly and isothermally from a pressure of 1.5 × 10⁻³ Newton per meter square to 5 × 10⁻² Newton per meter square. The change in entropy of the universe is. This is a trick question actually. Change in entropy of an ideal gas in an isothermal process is equal and opposite to the change in entropy of the surroundings. That is delta S of gas is equals to delta S of the minus of delta X of the surrounding. So, you can say that delta S of the universe, delta S of gas plus delta S of surrounding, that is 0 D. Now, let us talk about a little bit off the topic, not so important, but you should know entropy of the black hole. So, you just go through it, sometimes you get questions on this Planck length. A black hole is a cosmic object into which mass can only enter but it cannot leave. It is surrounded by a mathematical surface called event horizon, within which the escape velocity of particle exceeds the speed of light to make escape impossible. If you want to escape from a black hole, you need to have the velocity, such a velocity greater than the speed of light, which is impossible. That is why it is impossible to escape from a black hole. Since the mass of black hole can only increase, the area A of the event horizon also increases. Entropy of the black hole is given by this formula: S is equals to Kb times A by 4Lp whole square. Actually, this should be small kb, Boltzmann constant. 1.38 10 to the minus 23 joule per Kelvin. Here A is the area of the event horizon, surface area of the event horizon. LP is used here, that is called a Planck's length, which has a value root over h cut g by c cube. This expression is quite important. LP, Planck length, is equals to root over h cut g by c cube. C is in small. G is the universal gravitational constant. C is the speed of light, small c. 6.67 10 to the minus 11 Newton meter square kg to the minus 2, that is the gravitational constant. What is Planck length? Planck length is the smallest measurement of length with any meaning. It is roughly equal to LP, or about 10 to the power minus 20 times the size of a proton. So if you consider the size of a proton, it is like 1 by 10 to the power 20. So you can say this is the smallest possible length in any meaning. You cannot measure less than this. Now some imaginary picture of black hole. You can see we have the singularity, event horizon is this, that surface is denoted by A. Entropy of the black hole, S is equals to KB times A by 4 LP square. Where you have this LP is equals to root over h cut g upon. Okay, let's go for a very important thing, Gibbs entropy formula. This one is quite important for your examination. Let's say if you have a classical system, it means we have a collection of classical particles. With a discrete set of microstates. So if I consider, let's say, EI be the energy of the microstate I, let's say, then what will be the entropy of the system? Shannon entropy, actually this is known as Shannon entropy. Entropy can also be calculated from the number of microstate. So S is equals to minus KB sum over I Pi ln Pi. Okay, where what is this Pi? Pi is the probability of the system being in the ith level. Now you see, if a particular energy level has different states, so different microstates, if corresponds to single state, single energy, all of these state, let's say, by having a single energy, and there are gi number of micros degeneracy, then how this formula will get modified? If you consider for degenerate energy levels, multiple microstates correspond to the same energy. In that case, for degenerate level, this is for non-degenerate. Non-degenerate case. So, for degenerate level, the formula becomes S is equals to minus KB sum over I. Look, Pi ln, Pi was there, only it will be divided by Gy. That is the only difference we will have. Gi is the degeneracy. Of the ith level. So, how many states are having this energy Ei? That is the degeneracy Ei. Clear? So, with this formula, you may be asked to solve problem. Mostly the first formula is asked in your examination. Let me just give you some problem based on this formula. Any question from this? This is also known as Shannon entropy. If it is not, if there is no question, you can go for this problem. In a thermodynamic system in equilibrium, each molecule can exist in 3 possible states with probabilities half, 1/3 and 1/6 respectively. Entropy per molecule each. So just put in the formula. Probabilities are given to you. P1 is half, P2 is 1/3, P3 is 1/6. There is no degeneracy. So degeneracy is not coming into picture. So entropy is equals to minus KB sum over I Pi ln Pi. You just need to put it into the formula. So this is equals to minus KB times Pi is half ln half plus 1/3 ln 1/3 plus 1/6 ln 1/6. So this is half times ln 1 minus half times ln 2 plus 1/3 times ln 1 minus 1/3 times ln 3 plus 1/6 times ln 1 minus 6 times ln 6. So whenever you see ln 1, that is 0. So minus minus plus KB, what you have got, half times ln 2 plus half times ln 1/3 times ln 3 plus 1/6 times ln 6. Kb half times ln2 plus 1/3 times ln3. ln6 is, we can write ln2 into 2 into 3. So 1 by 6 times ln2 plus 1 by 6 times ln3. If I take ln2 common, you are getting half plus 1 by 6, and if I take ln3 common, 1/3 plus 1 by 6. Half plus 1 by 6, so 4 by 6. Yeah. 1/3 plus 1 by 6, 2 by 6, 2 plus 3 by 6. Kb 2 by 3 ln2 plus 1 by 2 ln3. That is matching with option C. Is it clear? Tell me. Okay. So let's talk about another very important formula, that is called Boltzmann entropy formula. In Boltzmann entropy formula, we find out the entropy. This is actually the statistical entropy formula. If you know the number of microstates, we can calculate the entropy using this formula. S is equals to Kb ln. This natural logarithm of omega. Omega is the number of microstates. So this formula you need to remember. S is equals to K ln omega. So I am giving you a problem based on this. Consider two systems A and B, each having two indistinguishable particles. In both the system, each particle can exist in states with energies 0, 1, 2 and 3 units with equal probability. Total energy of the combined system is 5 units. Assuming that the system A has energy 3 units and the system B has energy 2 units, the entropy of the system is Kb ln omega, value of lambda. Kb ln lambda, what is the value of lambda? Can you do it? You are given two systems A and B, and you have two particles in both the system, but they can exist in any of the four states. It can exist in 0, it can exist in 1, it can exist in 2, it can exist in 3. Same is true for the system B as well. And it is of equal probability. Total energy of the combined system is 5 units. Here in this state 0, energy 0, here it is energy is 1 unit, here it is energy 2 unit, here it is 3. So if you add this total, you will get it 5 units. So what does it mean? Let's say you have two particles, let's say P, Q, to accommodate in system A, R, S in accommodating system B. So you have to accommodate it in such a way that total energy comes 5 units. If you keep, let's say, P here, Q here, total energy from A is 3 units. So you have to keep R here, you have to keep S here. So you can see total energy 0 plus 3 plus 0 plus 2, so that is 5. Let's say you keep here Q, you keep here P, you have to keep S here, you have to keep R here. Again, it is 5 units. Let's say you keep P here, Q here, 1 plus 2 is 3, you need 2. So you can keep, let's say, R, S both at 1. So 2 plus 1, 3 plus 2, 5. Let's say if you keep here Q, if you keep here P, so 3 unit again. Here you can just keep it at RS. So here this is one combination. Here also you get the energy 5 minutes. Are you getting it? So you will try this problem at home. I am giving you at homework. I have given you sufficient hint. You will do it at home. So you have to calculate the entropy, right? The entropy is the total number of microstates. From this you can calculate the microstates. And from that you can get the entropy and you can find out the value of lambda. If it is not solved, I will share with the solution. Share with you the solution. Now look at this problem. A system of n interacting and indistinguishable particles of spin 1 is in thermal equilibrium, thermodynamic equilibrium, the entropy of the system. So to find out the entropy, we need the formula of S is equals to Kb ln omega. Omega, if we have spin 1 particle, what is the number of microstate? You know, it is the formula 2s plus 1 to the power n. N is the number of particles. Omega is the number of microstates. Where here you have given S is the spin of the particle. So 2 into S is half n number of particles, so to the power n. So this is 2 to the power n, and S is equals to Kb ln 2 to the power n. So n Kb ln 2. Acha, S is equals to 1, it is not half. So if S is equals to 1, it becomes 3. So it is matching with option D. Yes. Now one last thing, that is Gibbs paradox. Let's talk about that quickly, then we'll resolve the session. Mixing of two different ideal gases is an irreversible process resulting in an increase in entropy. This is a Gibbs paradox. So let's say we have two ideal gas. One ideal gas is A, another ideal gas is B. So for the first ideal gas, the specifications are, let's say there are n1 number of particles having volume V1 maintained at temperature T. Ideal gas B has n2 number of particles maintained at volume V2 and temperature T. Now when they will be mixed, there will be total n1 plus n2 number of particles, V1 plus V2 amount of volume, and a common temperature T, let's say. So what is the change in entropy? Delta S is equals to the entropy of the mixture minus entropy of the individual A and B. So we can use this formula of S is equals to n K ln B plus F of T. Using this formula, we can see this is, and S, you individually apply this formula K into n1 ln V1 plus n2 ln V2 plus n1 plus n2 Ft. Okay, we get K times n1 ln V by V1 plus K times n2 ln V by V2. This is greater than 0. So you can see there is an increase in entropy. So it gives us the result that the mixing of two different ideal gas resulting in an increase in entropy. That is a violation. If you put N1 is equals to N2 is equals to N, V1 is equals to V2 is equals to V2. For two ideal gas identical in composition and thermodynamic state, delta S is equals to, you still get a positive value. By putting N1 is equals to N2, V1 is equals to V2, you get 2K ln2. Since mixing of two identical gases does not create any state, this is the main thing. Since if you mix two ideal gases, no new state is created, that is why delta S should be 0, but from the calculation we are getting a positive value. This discrepancy is known as Gibbs paradox. Now, how this Gibbs paradox was resolved? It was resolved by replacing the sum of states of partition function z by n factorial. We will talk about partition function later on while discussing canonical ensemble and all. So, the partition function should be divided by n factorial to resolve the Gibbs paradox. And why it is divided by n factorial? Because you have n number of indistinguishable molecules. So, n factorial number of possible permutations among themselves do not give rise to physically distinct states. So, if you have, let us say, n number of distinguishable elements, so if you just take n factorial possible combinations or permutations, that will produce n factorial different permutations. But let us say if the n number of entities are all identical, indistinguishable from each other, then n factorial possible permutations will be basically one permutation. They are all identical. If you keep this one first, this one second, or this one first, or that one second, it will not change. The configuration is only one configuration. So, we are over counting n factorial. That is why if you divide by n factorial, that over counting issue is resolved and the Gibbs paradox is resolved. Okay. So, this one you can read. This is especially important for interview purpose. It will be uploaded to the course folder. So, don't worry. So, with this we end this session here, guys. We are already very late today. We are stopping here today. Thank you guys. Thank you very much for joining the session. Have a great day. Bye bye. Take care. See you in the next class.